River Architects back in 2003 when we were working outside of our apartment in New York City. But originally, I'm from the Hudson Valley and got my master's in architecture from SUNY Buffalo. And that was back in 1995 when I graduated. So I've spent about 15 years working in New York City in a variety of firms, mostly first kind of design firms, and then switched more to restoration and then technical firms, which were good primers for all the work that I've been doing in Passive House now. So I've been trained in doing Passive House for about 10 years. So I'm kind of an early adopter for that. And I recognize Passive House as being essential to addressing climate and carbon emissions in buildings, and it's kind of the only way that we as architects have the ability to greatly affect the outcome of the planet. So I think that's a pretty good task to undertake. And we're based in Cold Spring, New York, which is a small village on the Hudson River, just south of Route 84 and the city of Beacon, across the river from West Point. So it's a nice location to be. And we work throughout the tri-state area. We've got Passive House residential projects all over the Hudson Valley, as well as a few commercial buildings. Our own studio you see in the background here is a retrofit of a blacksmith shop that was built in about 1840, and we're source net zero, so we actually offset the emissions all the way of the grid, so all the way back to power generation sources. So we've been here in this building for about 4 years now, and it's a terrific place to be. Let's see, we've got projects in the Adirondacks and in a lot in the Catskill area, and a few in Connecticut as well. So we kind of get around. We also did the first certified passive house in the state of New Jersey too. So we've been heavily committed to doing this, and also to promoting Passive House as an organization. So I'm the founder of the Passive House Alliance Hudson Valley, which is a professional organization that helps train other architects and builders in Passive House as well as affecting policy. So we brought NYSERDA on board so that they're actually now funding a lot of different Passive House trainings, and in fact just sponsored and hosted the Theus conference in Tarrytown, and so in the Lower Hudson Valley. So bringing the North American Passive House community together. We had over 500 people in a 4-day conference there for that. So it was a good thing. And Yeah, so I'm gonna just start presenting on Passive House, and hopefully it's not completely new to everyone, and this will be um, both interesting and I don't know. Wish me luck.
Good luck.
Thank you. Okay, so you can see my screen now, right?
Yes.
Okay,
I'm just
and
going to make it larger for us here. There you go.
okay, great. So this you know industry is a mess. Transportation is a mess, but buildings are even worse in terms of carbon emissions. So buildings in the United States account for about 41% of the carbon emissions, and that's both including embodied carbon as well as operational carbon. So the amount of carbon that goes into creating buildings as well as what it takes to maintain a building through its lifetime. And so this is a major black spot on our profession, but it is an opportunity for us moving forward to address this problem. Okay, and of course this isn't working. Okay, I'm gonna have to scroll. So just looking at energy use, this is a little bit old, but not, it's still relevant. The United States is the highest carbon emitter, and Um, and when you look at it in terms of income, where we have other high income countries, like Germany and Japan, way down here, almost half of the carbon emissions per person as in the United States. So there's really no excuse for this high emission, situation. And when you think of it as kind of a um, an allotment of carbon that per person, when you average it out in the world, uh, Americans are such high consumers that we far outstrip our fair share of carbon. So as a country, we really have to address it. But again, the good news is that you're looking at these big yellow slices here of these pies, almost half of it falls into our lap. And these numbers are a little different from the previous slide, but you can see that in the 40 plus range of the carbon in the entire economy is allotted to buildings, and so this is our chance and our opportunity. So, thing about Passive House is that it's about reducing the energy wasted through the building envelope primarily. It's about creating balances between heat mostly, but also there are also cooling opportunities where we can prevent just the rampant loss of heat. So these glowing buildings to the left and right of this building in the center are, typical Brooklyn row houses, which are, similar to row houses in Albany and in Newburgh and throughout the state. And they represent, really kind of the legacy of architecture. And you can see how wasteful they are in relation to this one Passive House retrofit, and that's in the center there. That's the first brownstone retrofitted to Passive House standards. And you can see that the energy loss through the building is virtually nil. Um, and the history of it comes from the energy crisis of the 70s, and the first response to it was this Saskatchewan conservation house, which was really an experimental project in a very cold climate. But rather than just doing big solar, I'm going to just scroll down to this one. I actually know this man, Richard Levine. Rather than doing big solar collectors that kind of both fry and then freeze as they kind of cycle through the day, the idea uh, the conservation house, which is really kind of outlined first what a passive house should be, is to just to have modest amounts of solar heat gain, and to manage the losses and gains equally. So there's a solar thermal collector here, and shutters to help regulate heat loss during the day. And this is using off the shelf technology that was available back in the 70s, and now we've got much better techniques and materials available. So passive house is different from passive solar, which this is an example of, but the idea is about creating balance. So a conventional building, we can just look at it as, just leaky and, poorly insulated. And the principles of passive house are to basically to air seal it so that we um, eliminate the just free flow of energy through gaps and holes in the construction, which create two things. Energy loss is one thing, but it's also moisture transfer, which when you transfer moisture across a gradient, temperature gradient, you create condensation, which is a very big concern for durability. And so air sealing is a core principle both in keeping a building from basically rotting from its own occupant load, but also to conserve energy. Then after air sealing, insulation is critical, and protecting the building envelope, the insulation and the air sealing layers with a proper weather-tight shell. And now, what a critical thing though is that when we make airtight buildings, the occupants need to breathe. So early experiments in passive house were had a lot of problems with air quality and actually mold growth because of the rampant condensation as well as high levels of CO2. So introducing an ERV or enthalpy recovery ventilator, which helps move fresh air and moisture carefully so that heat from the interior space is recuperated or cooling during the summertime with the incoming fresh air, so that again we're establishing balance. So the fresh air ventilation has a very high efficiency rating in the 80 to 90% range, so that we're losing very little energy while at the same time we're giving very good, fresh, constant air to the inhabitants. And so kind of putting it all together diagrammatically, it's a simple structure with the fresh air ventilator here, a small, tiny little mechanical system for creating really backup heating or cooling. And an important aspect too is solar control. So these are things that you'll see eventually in the Cidery project as we get to it. So we ask a lot of a conventional building where we put both the aesthetic layers, both the exterior and interior sheathing layers, and the structure and the mechanical systems and the insulation all into one tiny little kind of component, typical 2x4 or 2x6 wall. And, there's a lot of opportunities for air leakage and for thermal leakage when we have all this stuff, kind of crammed together. Thermal bridging, so where the studs are, heat transfer is very easily accommodated, which is not a good thing. So in a passive house wall, we like to just kind of separate the services and the functions so that we get them each to do their job better. So we have a much more robust insulation layer, a dedicated service, and usually structural layer that allow those things to happen uninterrupted. A ventilation layer on the outside so that we handle moisture much better, so that the exterior wall finishes hold up longer. So this is what the actual wall looks like in practice. This is a section cut, plan cut through a typical passive house wall. So 2x4 structure, an airtight layer here, the insulation layer here with what we call Larson trusses, which are essentially I-joists set vertically. The thermal bridging of those little OSB layers is tiny to negligible, but we actually calculate that too in the heat flow calculations. So, a typical wall in New York State would be R19, or code is now adjusted a little bit to, okay, now I'm getting that feedback again. So, um, okay,
Turn down the volume of the TV a little bit, see if that helps.
that's weird because it just came out of nowhere. All right. So we typically see about an R19 wall for conventional construction, and we're R45 to even R60, 65 for a typical passive house wall. And just kind of looking through what the history of mechanical systems throughout North American history here. 19th century, people usually used wood or coal to heat their houses and put on a sweater. Then we made things extremely complicated and hard to run. And then passive house is really in a lot of ways coming back to those simple methodologies of the early days, but with good building science added to know that we can have more comfortable spaces and healthy spaces for people. So the energy losses, or the energy conserved is considerable for a passive house. We're typically saving 70 to 90% of the energy needed to heat or cool a building before any renewable power sources are included. So by doing a very well conserving building envelope and doing smart mechanical systems, we're able to drive the energy demand 70 to 90% lower than current code buildings. And so, it's really, again, about balance. In a conventional building, balance is obtained by, letting energy losses just kind of run high and then making up by, huge mechanical systems. And so our goal with passive house is to lower the energy and the envelope losses um, to such small manageable levels that essentially they're balanced by solar gain and internal loads, such as occupants giving off heat or the heat from our computers, so that the amount of energy needed to be added to the system is quite small. Um, and just looking at how these buildings perform, this is the Arctic vortex from January 2014, where there was a severe storm that basically knocked out the power grid for in some places for as much as 2 weeks. So when you have conventional buildings that lose power, um, people are immediately put into harm's way because the buildings can no longer sustain life essentially. So as soon as you know um, some climatic catastrophe happens, such as the snowstorm in Texas last year, or the polar inversion, or if there's a hurricane that comes and knocks out power, people are usually in a pretty bad way right off. But in a passive house, um, it's actually a um, there's a level of survivability, especially in cold climates, that it takes very little energy to heat or cool, and people are not put in harm's way and don't need to be evacuated. So the red line is showing the internal temperature, which in a lot of ways is completely separated from external temperature, which is this purple line. So it's a really I'm sorry, that's dew point. The black line is the external temperature. So you can see how different that is in terms of the, uh, the risk that people are put into. This is dropping down to near 0 degrees here, and at the same time, the internal heat loss is about there. Okay, and so this is just a graphic that we put together for our own building here. And I stole this from Europe, where they show these. They basically have a very clear graphic where you can see the energy performance of buildings. So they rate their buildings from G to A, and then I added this A plus, where we're actually net positive. So it's I think it's a good graphic that helps people see what's going on here. Um, these our numbers are a little bit different from what we ended up doing, but you can see R42 for walls and R63 for the roof. That's pretty close to what we have. And this is what the building looked at like before we renovated. So a little tiny commercial structure. It was actually rotting into the ground here. And this is what it looks like finished. So we raised the building off the foundation, and the goal was to originally extend up the stonework, but we discovered that the stone foundation was in really poor condition, so we actually lifted the building entirely off the foundations, slid the wood frame into the backyard, and redid the foundations entirely. But some of the details that I had developed for it. So you can see that the original timber frame is here, and then we air sealed over the top of the existing sheathing, and then did the same Larson trusses that I'd shown in that earlier diagram, both for the roof and for the walls. So so here it shows the walls as being sheetrocked, but we actually left the timber exposed. And this is an early detail where I'm showing the original stone foundations and then what we were planning to do to extend them. What we ended up doing was taking these out and then building the walls outward, so we actually gained an extra foot in each direction by redoing it, and then took, and eliminated this heavy overhang that was resultant from working with original foundations. So the end result was actually better than trying to work with the existing. But this is the building after we had redid the foundations and put it back onto the foundations, put the frame back on before we stripped away the fake shutters and all that. We actually have a thermal break between the timber frame and the concrete block who was doing all the heavy lifting of the structure. You can see right there, it's a 4-inch thick foam glass layer, so that we've eliminated thermal bridges entirely. So we had cut back the eaves so that I'm gonna just I gotta do something about this mic. It's killing me. Sorry. Okay, so we cut back the overhangs so that we simplified the structure so that we can air seal directly over. So this film was basically a peel and stick that we applied to the new sheathing that we put on over the timber frame, and we had left the original sheathing on the roof. It's not the true original. It's board sheathing underneath it. You can actually see in the space here. And by cutting back those eaves, we were able to really make this very simple to air seal and then to apply our Larson trusses over that. And these tubes here are light tubes that bring light in high into the roof system. They're placed actually where the original roof vents from the open forge that was in the middle of this space from the blacksmith days here. So these what we call Larson trusses are then wrapped in a blue fabric. You can see it starting over here, and then dense packed with cellulose insulation, so that it's like analogous to a puffy down jacket. And then we recreated the rafter tails so that we bring back the original look because we are in a National Historic District, and that was an important aspect to them. So the end result is that we have the timber frame as it was originally constructed, and how the original inhabitants used it for when it was the blacksmith shop. So we brought that bit of history back and kind of upgraded it to face the future where we have to stop using carbon in our buildings. We have a small solar array here, and we've got 10 computers, dual monitors, and and actually have an electric car that we charge as well, and we're source net zero. And this is just looking at our energy output from our solar versus our consumption. So our energy use is quite small. So when we have days of like rain and grayness throughout the year, it's offset by the days of really great production. The good thing about this too is that it's having this data available, we learn about energy monitoring, so we know when it's better to do things like run the dishwasher. So before we would either run the dishwasher early in the morning or late at night, the last person to leave, just out of habit. But then you realize that you're paying for electricity at this time, and we're demanding electricity from the grid, and it teaches us that we can manage that. So if we can take loads like a dishwasher or any other thing, like in a cidery, it might be an apple press, and move it into the times of peak energy generation, then we're taking less from the grid, and it's an important aspect to keep in mind. And this is what our production looks like over the course of a year. You can see all those green peaks outweigh those red peaks considerably. In the few days of bad weather, late January, early February, are through the course of a year are greatly offset. So that's the presentation on Passive House. And then if anybody has some questions or anything like that, I'm going to just pause the screen share while I queue up the other stuff on the studio.
All right, I had it on mute because I thought that might help the volume.
That helped a lot. Thank you. I appreciate it.
Did it? Okay.
Yeah,
Okay.
it's hard to keep track of your thoughts when you hear yourself.
Yeah. I finally figured that out. Okay. Any questions about Passive House? I'll pull them through so you can hear.
Great.
No questions, you guys? What do you guys think of Passive House?
Pretty cool.
You think it's pretty cool? Do you think it?
Yeah.
Do you think it starts to be like some of the reasons we talked about in general about how we have the spacing for the material and how we're talking about really thick walls and roofs for as we're drawing our sections and plans?
And
This
also
is-
about R value, can you explain a little bit for our students about the R value of materials that you use, for the passive house certified buildings?
Great, yeah. And so the materials we use for, for insulation, and I would imagine that you've all been, you've had classes on thermal dynamics so that you understand what an R value is and that it means resistance as opposed to conductors, which I don't remember. that the inverse of R value is a U value is about conductance. So for passive house, it's kind of it's neutral on what we may use for insulation, but there's a heavy preference on avoiding plastics and foam materials, and so again about lowering embodied energy. So we're heavily focused now, I would say, as a movement on not only conserving energy through the occupancy of a building, but addressing how much energy goes into building a building. So if we rely heavily on spray foam, for example, the embodied carbon is so high that some people have done calculations to say that it's as much as 500 years of energy performance we need to offset. So if that's how we address climate change, then forget it, we're done. It's not going to happen. So what we used in this is cellulose, which is a wood fiber based insulation, often from reclaimed, recycled paper products. So we're able to use something that traditionally is just wasted as a long-term insulation material. Sorry, that was long-winded.
No, I appreciate that because I'm not an expert in passive house, and we did talk a little about early in the semester about insulating on the outside of your building and all these things. And I brought, like, I know foam's not good, and I didn't have a great answer for how to place it. So I really like those slides in particular where you were showing those I-beams, whatever you call them, in the reverse orientation, the fabric, and then filling it with cellulose.
Great. Yeah.
Good idea. Yeah, we have a question out here.
So like using that different material, like how does fireproofing work? Like when you use that, what is it, fiber insulation or whatever, like.
So he's asking about the fire rating of a wall like that.
Great. Good question too. So cellulose is treated with boric acid, which is non-toxic. It's essentially a salt that is both flame retardant and insect retardant as well, repellent. So it's actually quite a good material in terms of thermal fire resistance. And in the case of our building, which you can see behind me with the exposed timber, we actually treated that with a flame stop product. So that renders it as a Class A fire resistant material. So, so there are ways to do it in a wood frame construction. There are other, like for high-rise buildings, the use of rock wool insulation has, extremely good fire protection properties. A good example of intentions gone bad is the Grenfell Tower fire in London a couple of years ago, where they had used foam insulation on the exterior of a building as a retrofit insulation material, and an internal fire in one of the apartments then set the entire facade on fire, which then entered into people's apartments and killed quite a lot of people. Like 80 people died that night. It's a disaster that I think the energy efficiency crowd took quite seriously, and thankfully the United States has higher testing requirements for flame spread, but avoiding foam is a really important decision, both not only for addressing climate and embodied energy, but also life safety too. And
Excuse me, what's the question? Did you say anything about the type of glass you- Oh, the question was, how are your windows holding up in the energy transfer, the R values of windows? What window types are you using? Things like that.
great question. So a lot of the windows we use almost exclusively are from Europe, but American manufacturers are starting to come online as well for this. They're triple pane windows with a greater airspace between the glass and often with argon or other inert materials that reduce the convective loop in between the glass. So a typical American window is about the equivalent of about an R2. Ours are between an R7 or 9. So they're um, they're much better than conventional windows, but at the same time, they still lose energy if we're not careful. So we are judicious in where we locate our windows. Usually they're on the south and avoid obviously north-facing windows or reduce them to a certain level. But it's actually east and west windows that can be the most problematic because the sun is coming in at low angles and really can be really challenging to control kind of rampant heat gain. When it's south facing, we can control it better because it's easier to predict. It's higher in the sky during the summertime, so it's a lot easier to cut off like too much solar heat gain. Low in the wintertime, so we get the solar gain that we want. And we can model all of that. So that fits into our energy models quite well. But those eastern and western sun angles can be really challenging because it's too much sun all the time.
Yes.
So like money wise, would you say building like I want to say like yes, you passive house itself like saves energy, but what about money? Like is it more expensive to still build a passive house?
Hey, how much of an upcharge is it to build a passive house? And then how much do you save on the back end from the energy savings?
Um, that's a good question. What we're seeing is that passive houses for smaller buildings in the neighborhood of about 10% more, depending on the complexity and also the skill of the builder. But others are, we're starting to see those numbers come down from about 10 or even 12% more to like 5% or 3%. And as the buildings get bigger, the cost differential gets smaller and actually can reverse because you're seeing large multifamily apartment buildings in New York City or in Portland, Oregon, for example, that actually cost less to build because the mechanical systems get so small. So it's passive house is tough on the smaller scale. So like my building is challenging, but as buildings get larger and larger, there's a cost savings because mechanicals are just almost non-existent. They're so small.
I'm reading the new Bill Gates book right now, and I'm not going to get the number right, but something that stood out to me, I think, in the discussion of cost is something like if you just take carbon as the problem, and we have technology that can pull carbon out of the atmosphere. If you run those costs, we're sitting at something $5 trillion a year of the cost by putting the carbon in. And if you calculate that in, like at some point in time, if we keep going the same way we're going, we are going to have to start paying that $5 trillion a year across the board. So you factor that in, all of a sudden you're saving tons of money.
Exactly. It's it's also when we go back to that slide, that early slide where I was showing the cost, the carbon per capita expenditures, and that the United States were far outstrip everyone else in terms of carbon consumption. And so if we think of carbon consumption as like our fair share, we have to really we have got a lot of atonement to make. The by If we think of carbon as an allotment, we're deferring the cost of carbon on the rest of the planet, and so like by consuming here, we're creating an expense for someone else, if you think of it. Countries that have to relocate because the entire island nations are being will be underwater in 50 years, or the cost of famine and flood and war. So those are things that are expenses of rampant use of carbon, and thinking of it in purely in terms of dollars of construction is actually quite harmful. And yeah, so there are some calculations that people have done of the amount of consumption that we're doing on planet Earth right now. We're on a trajectory of consuming something like 7 Earth's worth of resources. So we need to restore a balance where we're not outstripping the living capacity of the Earth in supporting our lifestyle. If we're consuming at a rate that we use our resources of the planet 7 times over, then it's going to be an entirely dead planet in a few generations. So
Other questions about passive house? Should we jump into the Cidery presentation? I think we're ready for that. You ready for the Cidery?
great. Yeah, let me queue up here.
Okay, I'm gonna just put this one on mute so you don't hear the feedback for this.
Excellent. Great. So I hope, let's see how things go here. Hopefully things won't jump around in some weird way, but let's see. Okay, how's that? So this is our Cidery. I gave this presentation at the FIAS conference just at the beginning of this month. And we just completed this this past winter, so it's now fully occupied. This is a new construction, and it's in Callicoon, New York, in the Western Catskills. Oops, let's see how that. Okay, let's hope this behaves for me. For some reason, this is not scrolling. Okay.
The TV cut out on us, so we didn't hear the last minute.
Okay. So
and this
I'm
one's
having-
on mute, so hold on. Let me do this. I'm gonna try this. Okay, I think you're back. Can you see-
Okay. Great.
Yeah.
All right.
All right,
so
good.
I am. I'm having some technical issues. Oh, okay, now I got it worked out. I have to relaunch my share.
Okay.
Okay, I'm good
There
at
you go.
this. Okay, here we go. All right. So
All right. All right. Good.
sorry. So our Cidery project, we completed this this past winter. I've given this presentation at the FIAS conference in Tarrytown just the start of this month. It's roughly 9,000 square foot building that's both event space and tasting upstairs and production down at the lower level. So let's kind of talk to you about who we are and what we're doing. And so our our cidery is the world's first fermented beverage passive house in the world. So like we've beaten out all the breweries and wineries and other cideries throughout the world. We were approached by the Doge family, who is a multi-generational family in Callicoon. They've been there for I think 4 generations, and have a long history of apples in their family, including some bootlegging as well, when they're making cider during the prohibition. They embrace the idea of doing organic orchards there. So this guy kneeling here, his name is Mike. He's considered the grandfather of organic apples in North America, and the legacy of orchards and apples in particular is a good one, where the United States is originally had thousands of varieties of apples. I think there were 10,000 varieties in Appalachia alone. And so there's a huge variety of apples produced for various different uses, but primarily for drinking, making cider. And and so here's how they did it back in the old days. In Callicoon, they actually used to have community presses where people would bring their own apples from their own orchards and press them for making cider. And this is one of the cider, the orchards at Seminary Hill Cider. This one is actually, you can't really see the cables in here, but you can see the posts. This is they have this tension line to train the trees onto the apples, and they grow them much more like grapes, so they can grow them very close together. And you can see that they allow for wildflowers and co-plantings to happen, so that it's a much more natural environment and more biodiverse than a conventional orchard, which makes for actually healthier apples and healthier people. There's the seminary in the background that's the namesake of the farm, and the Delaware River a little bit in beyond. And this is the orchard, obviously very early on. What you can see here is the co-planting that's done. All the tulips and daffodils are planted around the trees because it actually keeps voles from digging through in the wintertime and harming the trees. The voles are rodents that will gnaw the bark off of a tree and kill it. And so the bulb plants actually uh, uh, persuade the voles to go elsewhere. And so here they are pressing apples in the space. It's very different technology, but from the old days, but the same efforts. They bring in apples in bulk off the fields, press them with the machinery, and then put them into fermenters for the production. For the building space, I was inspired by the barns, the historic barns that you see through the Hudson Valley. In this case, um, a, a bank barn nearby. It's actually quite close to you guys in Delhi. Um, and so that was kind of the inspiration. The gapped boards of the original banks or barns were to allow for drying of hay, so that those walls acted as a rain screen, essentially to allow to shed water, but also to allow a lot of air movement through to keep the hay from getting wet and to dry, so that it's useful throughout the year and actually prevents fires from spontaneous combustion. A different barn nearby that I was looking at as kind of inspiration. So taking advantage of the steeply sloped site, that you can have entrances on different levels and for different functions. And yeah, so that's the cidery again. This is actually a western view, and remember what I was saying about limiting the amount of sun that comes through those western windows. I wanted to create an opportunity for light to come in halfway into the building, so I actually created this peek out window so that I turned basically a western orientation into a southern orientation in terms of light, and it actually worked well for the views too. Um, and so the building is, this is the approach to the tasting and event space upstairs, and the cider production is down below. Site plan, it's a little hard to read here, but you can. Here's the access road. It's uphill, and then it's all downslope to the orchards here. So the apples are brought in at the lower level, and trucking is there, and the public approaches from the top. It's very hard to see here, but this is the construction plans of the tasting space. So here's that entry porch there, and the main entrance into the space. On the main tasting room and that peek out window there, a commercial kitchen and a tasting bar area there, and then restrooms and changing space there. Stairs that go down to the lower level, and another kind of dining space, and then that rear balcony that looks out across the valley, and then actually an outdoor dining space here that's the roof of an aging cave that's actually non-conditioned space in terms of mechanical systems, but it's built into the hillside and taking advantage of that of the constant temperature of the earth, and then plus essentially a green roof on top of it. Um, okay, and then this is the lower level. So this is the cidery production space. So here is our apple pressing area where you saw the photos, that one photo of. And then this is the fermentation area. And so these are the vats where the cider making happens. You can see here these dashed lines which indicate the floor drains. So the floor slabs are pitched towards the center drain, so that where everything is washable, and if a fermenter or a vat leaks, it goes into the drain and doesn't create any kind of problems. You can see that that happens in several different places, and also inside of the walk-in cooler, which is this large piece here. Typically, the fermentation happens at about 50 to 55 degrees. Again, so that ground temperature really works well for that. And then they use the walk-in cooler for actually, once the fermentation is complete, then they'll actually put it in there to cool it off so that it actually stops the fermentation process. And they have vats in there, or they'll have full kegs or full bottles as well, waiting for delivery that they'll store in there. Um, and over here we have a locker space, but also a laboratory, which is really important. That's where they may maintain yeast cultures for certain flavors, but they'll also test for the specific weight of the liquids, which will determine the alcohol content. So an important aspect to it. And hygiene is really important, so they're constantly washing. So the lower level is waterproofed up to 8 feet high up the walls, and so it's really just like essentially a clean bathtub inside of there. This is that aging cave, and we call it a cave, but it's a human-made space, but essentially the function is the same as a cave. And then this is a section cut through, again, the upper level with the tasting space, the storage cave, and then the production space down below. And here you can see actually a little bit of the thermal envelope. Because the upper space is really made for human comfort, this is one climate zone. The lower space is made for fermentation and apple storage, and so that's a separate climate zone here. And so you see the insulation layer across there. It's got its own airtight layer here. So this is one envelope, and the upper level is airtight and insulated. Here you can see the insulation running through the deep trusses of the roof there, and here we've got actually structural insulating panels for this part of the enclosure here. And there's actually no insulation under the slab and very little insulation in the walls here, because we're looking for that ground contact, so that constant temperature coming of the earth, about 55 degrees, is creating all the conditioning that we need for that space. So again, human comfort, apple comfort. So the interface of the two. And we use WFI models, which is an energy simulation software that takes into the our values of our products, the solar orientation, the performance of equipment, and that really helps us calculate the balances. So here you can actually see these green arrows. It's showing basically the heat flux through the windows, which is an important aspect there. And the stair tower connecting the two spaces is actually part of the thermal envelope of the lower level. So we have actually airtight doors and insulation there to separate that from the upper space here. And that's that. Here's the cidery under construction. That red kind of Martian earth look is actually the local blue stone, as they call it. But here it's got a red color. But it took actually quite a lot of blasting to create this hole for the excavation. Um, so our wall systems, we have concrete with actually a glass additive, an expanded glass additive that makes the concrete insulative and also lighter. So it's actually it's a more sustainable choice than conventional construction concrete. And here, in spite of what I had said about avoiding foam, there's sometimes we also have to look at the cost of things, and so we have EPS foam for the structural insulating panels, which are basically a sandwich of foam with a skin on it on either side. So in this case, it's an OSB skin on both sides. EPS is actually a better choice than other types of foam, such as poly polyisocyanurate or XPS, extruded polystyrene. EPS foam has different blowing agents chemistry that has a much smaller global warming potential. We have a timber structure that's set inside of that, and that's you've seen that in the well, you'll see more of that. So here's the insulation and the air tightness layer at the stair tower, and down below the exposed concrete with the additive. All the steel work that we actually had that galvanized before is brought in so that we don't have durability issues. You can also see the air tightness layer here, this Intello fabric there that creates the air tightness and the air control so that we don't have leaking between spaces. And then the timber of the upstairs is actually set on these green pads, which are a high compressive strength thermal break. So it's essentially a type of foam that has very high compressive resistance, so that we're actually able to bear the structure on it and still avoid thermal bridging. And here you can see it outside. This is the bracket that supports that peek out window. So these brackets are actually stainless steel, because both for durability, but also for conductivity. So stainless steel has much lower conductance than carbon steel. And then foam with ties that are supporting the facade of stone. And these ties are actually thermally broken too, so we're reducing the amount of conductance through these structural ties. The garage doors are actually high performance doors, and everyone knows from their parents' garage doors that they can be leaky and miserable. These ones are actually we're able to meet our very tight air tightness and thermal performance requirements. And it's really important to make sure that where the windows come in, that their air tightness is maintained, so that we don't have leaks around the sashes and all that. So we use liquid air barriers and tapes to do that. So here's a shot, soon after the excavation. Actually, you can see it makes a little more sense in terms of the scale of it. But the formwork for the foundations, it was quite tall, and originally we were going to use insulated concrete forms, which is basically like 2 layers of EPS foam that have plastic ties that go through it that the concrete is cast into. And insulating concrete forms, or ICFs as they're known, get kind of stacked up like Lego blocks, and then concrete is poured in between. But the risk of those in high walls like this is that they can actually burst, and those blowouts can be a really big problem on a job site. So our concrete guys were very nervous about that. So switching to this expanded glass product simplified the concrete pours. We were able to use conventional formwork, so it was less risky. So the glass beads are poured directly into the concrete mix. They have a decent they added a decent level of insulation that converts the concrete essentially from a net conductor to a net insulator. It's not a huge thing, but it's actually its conductance is actually better than wood. So it's a it's an upgrade. And it's really, again, standard concrete forms. It's just simply added in this bag here into the mixing truck and then poured into place. We had the timbers were all made off-site as well as the SIPs, so that all of this aided in the construction time. It was a really hard winter that we built through, which created a lot of problems. All that snow was hard to manage, and it created some water intrusion problems when we were kind of in vulnerable stages, but we made it through. But you can see the pre-cut, pre-shaped. These are coming directly from the factory with the windows pre-cut into them, and the splines and things that are structurally necessary for them are done in the factory. So it just gets picked off of trailers and set with a crane onto the site. Again, the heavy timber came from the factory actually, even with a coat of finish on it, and the steel connectors all done in the shop, so it was much better controlled. We had standing seam metal, which really receives the solar array quite well, and then our rain screen on the outside there, and then the finished wood is actually reclaimed from the old Tappan Zee Bridge that was demolished. There were actually wood pilings that were surrounding each of the piers of the bridge to keep ships from damaging them. Those were actually old growth larch from New York State that we were able to purchase. A mill had bought all of the timber that was pulled out from these, and it was over 1 million board feet, and so we were able to use that. It's naturally rot resistant and beautiful, and it's locally sourced sustainable wood. And standing seam metal because it's cheaper. These are the inlet and the outlet of the fresh air ventilation for the building, and so these manage all of the air for the upstairs, which is a challenge because a cidery, the tasting room might have, maybe 2 or 3 people there during the day when you have the kitchen staff prepping for meals. But then with an event, you might have 200 people in there at one time. So the mechanical system had to accommodate that. One of the things that we've done was actually, instead of using conventional gas burners that you would see in a kitchen, we used induction burners. So that resulted in us not needing to vent the kitchen to the outside, which is a huge energy loss in any kind of mechanical system. And this actually creates more flexibility for the kitchen, so that they prefer this over like a large six burner. This hood over the convection oven here is a recirculating hood, so it's got carbon filters that, so if somebody burns the toast, it doesn't smoke out the whole space. But by eliminating a vent through the roof, we're able to save drastically on energy performance, and also meet our air tightness goals. And this is the entire mechanical plant for the building. We've got 4 outside air handling units for the heat pump, and 2 that are actually water-based that help with the space conditioning and the refrigeration in the lower production space. The water-based one actually gives us it works better in the lower temperature range that space is conditioned to, while the air source heat pumps are really made for like regular human comfort zone. And so this is a diagram of the fresh air ventilation. It's fairly complicated, mostly because of the huge range in the occupancy. And this is what the space looks like, and you can actually see the Delaware River winding around out here, and some handmade tiles and zinc bar top, and some more of the reclaimed wood from the Tappan Zee Bridge. And then the lower level, so these are the fermentation vessels. They're small because they're kind of ramping up in production. But they have the space, the height to go to much larger vessels as their business grows. But you can see what the linear drains look like in the floor, and then the pitch to them is quite low, so it's doesn't feel unnatural to in there. Um, and then you can see the raw concrete above. One of the big challenges in cider making is that they use a lot of CO2 in the process. So what'll happen is they use CO2 to flush the fermentation tanks when they are basically draining out the cider as they make it, and they use the CO2 to keep oxygen from entering the tank and creating the opportunity for bacteria to grow. So the CO2 helps control what is happening in the tanks so that they don't have because they need predictability in making the product. The CO2 that we're talking about is not fossil fuel based, but it's just the natural CO2 that comes in a bottled form from manufacturers, so that they have that for their production. The fermentation process itself also kicks off a lot of CO2 as well, but that's easier to manage than this wholesale, just like flooding these tanks and then basically letting that dump back out when they fill the tanks again with the apple juice. And that was a big challenge for us to manage because this is very, very high. 2,000 parts per million will put people to sleep. So we really want it, no more than 800 parts per million, and even that's considered high. So this is too high for the ventilation system to keep up with. So when they do these purges of these tanks, we just came up with this simple solution of just running hoses and an inline fan to suck the air out at those the points of high concentration, and it only happens a few times of the year anyway. So. But just kind of working through the construction, you can see the underside of the sheathing that was actually used for the air tightness and the timber, and then what it looks like complete. And yeah, so we had a really great team of people. We work with certified passive house builders and raters and verifiers for doing all the testing. We got some really great publications. We were published in Metropolis Magazine, in Architecture Magazine, Design Online Magazine, and some others. And we won the Planet Positive Award from Metropolis in their hospitality division, and we also were awarded a design award at the FIAS conference for this project too. And that's it.
I'm gonna see if there's any more questions from our students here about the cidery. Any questions? Yes.
And what, there weren't too many partitions, is that a design choice or is this an ability choice?
There weren't too many partitions in the plan. Is that a design choice or sustainability choice?
More of a design choice because it created a lot more flexibility. If we had a lot of partitions, you really kind of lock yourself into a function. But in terms of the cidery production space, you want it to be as open as possible because they're moving a lot of equipment and often, with using either forklifts or lifts from tractors actually, and the apple crates are really big and cumbersome, so they need a lot of room to swing around. So making it as column free as possible is actually desirable too. So very few partitions, and if you can, the least amount of columns too. The other thing that I've learned, so that this is our first cidery, but we've done 3 breweries prior to this, and it's a very similar process, with the exception that breweries have what they call the brew house area, which where you need to cook down the grain in order to get the juices that then ferment. Since apples are, you crush them and it creates the juice, which is basically the stock that then becomes fermented. It's in a lot of ways a simpler process. So you go directly into putting it into tanks, and those fermentation tanks vary in size, and it's really good to create the opportunity for flexibility, because all of the best planning in the beginning usually goes out the window in their first year. They start to rearrange equipment, order new stuff. Usually they realize that they want to produce more than they had planned, and so having the space as open and flexible as possible is really important.
Good. Other questions? Yes. The question was how much ventilation is needed in the cidery component of the structure, of the production area.
Good question. I'm not really prepared to answer that one. I mean,
That's all right.
yeah, you definitely need to ventilate it. And it's especially, again, if you're making a passive house, you need to move air, because a lot of times a lot of cider makers start off using old dairy barns, which is pretty scary because the air quality is really bad. Um, so you want to make it a very controlled environment, which also means really good ventilation.
Yes.
What about like accessibility? I don't know if I saw like any, I guess, ground level floors on the building. Like I just saw a lot of stairs. Like maybe I just didn't see it.
The question was accessibility.
Good question.
How did you address that? Yeah.
Yeah, so the building is fully accessible. We have accessible ramps at the entrance to the upper level, and the lower level also has an accessible entrance into the space from below. And all of the thresholds meet accessibility requirements. We actually don't do thresholds on interior doors because that's just another hindrance. But all of the entrance doors have accessible thresholds and dimensions, as well as hardware. All the bathrooms are outfitted properly for ADA. The only thing, those stairs are a convenience stair, so linking them. But if an employee of the cider was had limited mobility, then that would be addressed by accessing the door from the space from below or above.
I have a question, which is there in this building, is there any connection of the visitors to being able to see how cider is made, a tour, a viewing window, anything like that?
Yeah, that's great. And that's exactly why we have those stairs linking the two spaces. Having the intent originally was to have a viewing window from above, but that was really tough to work out programmatically. So we created the opportunity to walk down those stairs to do tours and to view it from the upper level of the stairs as well. I should have included a slide of that, but I didn't. It's definitely an enjoyable thing to be able to see. One of our breweries, the Hudson Valley Brewery, which is in an old industrial building in Beacon, New York, has viewing windows from the event space down into the brewery itself.
Nice. Good. Other questions? Do you have any questions, Dr. Sofai?
Oh,
Yeah.
no, I'm good.
You're good? Yes, you got another question out here.
I have one more.
One more.
Related
Okay.
to kind of the positive, but not so much the cidery.
That's all right.
Is hydroelectricity something that you work with at all? Not sure if it's-
He asked if you ever worked with hydro electricity or just solar. I guess on-site hydro is maybe the question. Maybe we could throw in wind or any other energy besides solar. Or have you just worked with solar?
Great question. our options for hydro is really very site specific. We did have a client whose own house, um, he had a small waterfall that he was actually able to tap into, and he had a 7 kilowatt um, generating plant there, which is pretty good for residential. Um, but we've never done uh, hydro, like micro turbines like that ourselves for a project, and we've never done micro wind turbines, although it's certainly something we're interested in. Solar is really cheap now. The cost of solar has plummeted to where it's actually cheaper than conventionally powered electricity, and with the rebates both from New York State and the federal government, the cost of an installation is a fraction, and it drops every year. Um, Other opportunities for power generation might be a combined heat and power plant, which you can actually use, biomass to as a fuel stock that can create heat that's useful for space conditioning. It could be heat that's used for heating hot water, because hot water is always a big demand in a production facility, for mostly for washing, and washing down the space and washing equipment. But then basically it's using heat to generate electricity as well. So there are opportunities to use biomass as a generation source.
We have a question. It's a type of general question, but it's about the type of your PV that you use. And as far as I understand, you use that PVs on the roof in different size.
Mhm.
I mean, toward different orientations. Could you please explain a little bit about this?
Great, yeah. So we get the most solar generation on a south-facing orientation, but if we actually have the solar panels arranged in different facets of a building, so if we have like eastern and western oriented solar panels, then we actually can flatten that production curve a bit. So we get that very steep bell curve that you saw on the solar panels from my building. But if we have them on eastern and western facing facades of a building, then we can actually spread that out greater through the day. So we have a less pronounced peak, but it's a wider, more kind of, a wider base to it, so that we're able to create power through a longer period of the day. It's actually an important aspect. The challenge of solar power generation is that as it gets more widely adopted, we're going to have too much electricity generated at noon, and then that's going to create deficits in the morning and in the evening, because it's not, we have like such a high peak in the middle, but the demand is throughout the day, and so that creates the demand for what they call peaker plants, which are power generation to provide electricity when either the sun isn't shining, or that it's nighttime. And that's a challenge, is coming up with ways to distribute that throughout the day, and different orientations of solar panels help with that, as well as wind, water, and also energy storage, so batteries, or potential energy storage as well.
Good.
Great.
Else? If not, let's give them a round of applause. This was great. I think it helped the students understand sustainability, passive house, and help to understand cideries and all this. And so hopefully this goes forward. I'm just throwing this out there. Maybe, I know it'd have to be over Zoom, but maybe you want to sit on our final presentations in December. We can invite you to that.
Yeah.
That'd be fun. I'd be glad to. Yeah.
Yeah.
Thanks.
So, but we'll see if I can figure out. But yeah, this was great.
Thank you
So
so
we really
much.
appreciate it.
Good. Thank you. And I'll introduce you as well to the cider maker too. If you,
Okay. Yeah, that'd be great.
Great. Very
Yeah.
good. Thanks. Bye. Good luck.
Thanks. All right. Thanks. I gotta stop recording.